This is the overall hardware setup for the project titled Design and Control of Electric Powertrain by using Advanced Power Electronic Interface. In this project, the concept of APEI, that is Advanced Power Electronic Interface, is proposed. The APEI, that is Advanced Power Electronic Interface, combines BMDIC plus ESI. BMDIC is bidirectional multi-device interleaved DC-DC converter and ESI is 8-switch inverter. So in this project, we have combined the bidirectional BMDIC, bidirectional multi-device interleaved DC-DC converter and ESI, that is 8-switch inverter. Now we'll see the hardware blocks in detail. The first block is the microcontroller block. The 4 switches here and the first 4 switches here together form the bidirectional multi-device interleaved DC-DC converter. The 6 switches here and the 2 switches from this board together form the 8-switch inverter. And this is the 3-phase resistive load across which will verify the inverter output, and this is the single phase. The 8-switch inverter will give both 3-phase output. From these 6 switches we will get 3-phase output, and from this 2 switches we will get a single phase output. The input to this circuit is a battery of 12 volts. In the first microcontroller block, we have used PIC16F877A microcontroller, which is a 40-pin IC. The operating voltage of microcontroller is 5 volts. The input to this block is given through the battery of 12 volts. From that 12 volts, only 5 volts is given to this microcontroller using the regulator IC 7805. This is a crystal oscillator for clock pulses. So the output of the microcontroller is used to trigger all the switches present in the DC-DC converter as well as the 8-switch inverter. Next block is the bidirectional multi-device interleaved DC-DC converter. The 4 switches here and the 4 switches here combine to form the DC-DC converter. The 4 switches are MOSFET IRF 840. This is the resistive load across which will verify the output, the boosted output of the DC-DC converter. The input will be boosted in this DC-DC converter. The next is the 8-switch inverter in which will first combine the 6 switches and the 2 switches from this board. So totally 8-switch inverter. These 6 switches will give you the output of 3-phase inverter, and these 2 switches will give the input of single phase. And these 3 will be the resistive load wherein we will verify the output from the inverter. The 3 phases RYB will be verified, and this will be the point wherein we'll add the motor and see it's running. We'll also check a load of lamp and see how it runs. In the first direction, the input of battery would be given to the circuit. The input from the battery would be boosted through this DC-DC converter, and the output from the DC-DC converter will be given to the inverter. This inverter output would be verified in the 3-phase resistive load and in the single phase. Now, in the second direction, we'll assume that there is no input from the battery. So, we'll remove the battery in the second part, and in this part we'll add the grid. This for showing the grid, we have added a connection from the transformer. So we'll add the connection. In this part, we'll assume that only the grid is working. There's no input from the battery side, and through the grid the inverter will work, and from the inverter the DC to DC converter will work. So the first direction is to be assumed as vehicle to grid. The battery voltage we assume is from the vehicle to grid, and we'll add a motor here at this point where we have given it as M, and we'll assume that the vehicle is running. And in case when there is no battery input, we'll take the supply from the grid, and from the grid it will go to the inverter, and from the inverter to the DC-DC converter. Now we'll switch on the circuit and see how it operates. We have switched on the circuit and we can see the LED is glowing. This shows that the circuit is working. We have connected the input to a battery. The red is connected to red and black is connected to black. They should not get short. They should not touch each other. The input from the battery is given to the microcontroller board. The output from the microcontroller is used to trigger these switches, and the 12 volt is boosted across this DC-DC converter. We can see a boosted output across this resistor, and we'll be able to see a 3-phase inverter output being displayed in this RYB. The probes of the DSO is connected across R and Y, and we can see an inverter output being displayed in the DSO. And we can even verify the DC-DC output also can be verified. It is boosted to around 26 to 27 volts. And this is the inverter output. DC output here, the inverter output. And now we'll see a load running. We've added a you can see a lamp glowing. This is the load. So the load is running, lamp is glowing. Now we'll check the operation of a motor across this. At this point where it is written as M, we can see that the motor is also running. Now we'll see the reverse mode, wherein the input from battery would not be there and we'll get the supply from the grid. So this is the forward mode, wherein the lamp load was running and motor is running, and we have also verified the inverter output. Now the reverse mode would be verified, wherein the input from the battery is disconnected. So there is no input from the battery side. We have removed the motor also. Now we have inserted a output from the transformer. This is, we assume, as input from the grid, and this has to be connected where we have given it as T. So now we are in this condition, we are getting input only from the. Now we will verify the reverse mode, wherein the supply is only from the grid. A connection from the transformer is plugged in to the point where it is written as T. So this is the input from the grid, and the input from the battery is removed, and from this grid it will go to the inverter, from the inverter to the DC-DC converter, and we have connected the probes of the multimeter across the DC-DC converter, and we can see it is around 14 volts. This input from the DC-DC converter can be used to charge the battery in the reverse mode. So in the forward mode, we are getting an input from the battery. It goes to the DC-DC converter, then to the inverter, and there from the inverter output, we'll take 3 resistive loads to verify its output. We have run a motor and also a lamp, and in the reverse direction, the input from the battery is removed. So when there is no source from the battery, the grid supplies the input from the grid, goes to the inverter, inverter to DC-DC converter. We're getting around 14 volts. This input from the DC converter can be used to charge the battery. This is design and control of electric powertrain by using advanced power electronic interface.